In the first video, I showed that IBGR is testable, internally consistent, and that it can produce measurable differences verified by concrete numerical runs. In this video, I'm not going to repeat the data and plots in detail. This is about the consequences. What would it mean if this direction is actually right? The goal is simple: to think clearly about what follows if a late-time effective deviation in the gravitational response is really present in our universe, and how that could reshape the way we look at late-time structure growth, the why now problem, the interpretation of the dark components, the information tensions around black holes, and the possibility that the link between quantum physics and geometry is not a random conflict, but part of a deeper connection. So let's assume this idea is not just an interesting thought. Let's assume it has a real physical footprint. That gravity at late times does not only depend on how much matter exists, but also on how matter is organized into structure. If that is true, then we haven't found just a tiny tweak. We may have found a new viewpoint. Before we go deeper, let's set a clean frame. Standard cosmology is extremely well tested in many places, but there are areas where the picture does not fully close. There are open questions about the earliest epochs, and there are tensions in late-time observations as well. I'm not claiming that we should replace everything. What I am saying is this: there is a viewpoint that adds a deeper layer to the same story through organization and physical information. And this is not something invented out of thin air. It's not a story added afterwards. It's a direction that could first be captured numerically, because in this picture, gravity is not a rigid rule that must look identical in every environment. It can be a response, a macroscopic reaction, an effective law, not because gravity is not real, but because the universe is not an ideal homogeneous dust. It is a developing, self-organizing system. And when I say information, I don't mean anything mystical. I mean structure, distinguishability, correlations, patterns, the cosmic web. This is an effective, late-time description. It is not a new fundamental field. And it is not an ontological claim that everything is information. And here is the minimal statement we can actually compute. The same average matter content can lead to a different effective gravitational response if the late-time structure and correlations are different. And this is not just philosophy. In the numerical runs, it shows up concretely. The strength of structures changes, the growth rate changes, and combined observables shift, the ones that capture galaxy motions and lensing signals at the same time. From this point on, the question is no longer, is this idea beautiful? The question is, what follows from it? Let's start where many modern tensions concentrate: late-time growth measurements. The standard picture is simple. There is matter, there is gravity, there is expansion, and together they build cosmic structure. But when we measure the late universe with high precision, we find that some observations do not tell exactly the same growth story, as if the late universe builds structure a little more slowly than the simplest model would predict. The usual reaction is to say, something is missing: a new particle, a new component, a new field. But if gravity is a response, then another possibility appears. Maybe we are not missing ingredients. Maybe gravity does not change everywhere. Maybe the response becomes different in an environment where structure and correlations are already strong. And if that is true, then some late-time anomalies are not necessarily missing components. They could be traces of an effective response physics. And there is a key consequence here. This is not based on a single signal. Multiple channels can cross-check each other. There is weak gravitational lensing, which is sensitive to late-time structure. There is RSD, where the growth rate is measured through galaxy motions. And there are consistency tests that connect growth and lensing and ask whether the picture closes. And finally, there is the strongest control: how all of this fits with the full CMB lensing signal. So this is not about finding one strange number. It is about multiple independent probes potentially pointing in the same direction. And this leads directly to the next big question: why do these tensions show up late? Why not earlier? The standard answer is because dark energy becomes dominant at late times. But here's another possibility. Maybe the epoch where an effective gravitational response can deviate and the epoch of complex structure do not overlap by accident. Not necessarily cause and effect, but possibly two sides of the same process. As the universe becomes more structured, it carries more patterns, more correlations, more distinguishability in its state. And that is exactly where an information-sensitive response could become macroscopically visible. And if that is true, then the why now problem is not just an embarrassing coincidence. It could be a signal that the late universe is entering a different kind of regime. And this brings us to dark matter and dark energy. It's important to be clear, this does not mean there is no dark matter, and it does not mean there is no dark energy. It means that, at least in the late universe, some of the anomalies may not be direct evidence for new ingredients. They may be a small but real deviation in the effective gravitational response. From here, we move into a more interpretive domain. This is not a derivation. This is a map. What could this viewpoint suggest? The timeline of the standard cosmological model takes us from a hot, simple beginning to galaxies and the cosmic web. And many of those steps are extremely well tested. But the deepest questions begin where we are no longer just measuring numbers, but trying to understand what they mean. Imagine the early universe as almost perfectly simple. Very little difference, very little distinguishability, very little structure. Then small asymmetries appear. And from that moment, the universe is no longer silent. It is no longer identical everywhere. Structure formation begins. Small differences grow into a network. A network becomes large-scale structure. A structure becomes the cosmic web. Galaxies, clusters, filaments, voids. And here is a conceptual bridge to time. We often imagine time as something external that simply flows, but there is another viewpoint. Time becomes physically meaningful when there is change, when there is before and after, when something happens that cannot be undone without leaving traces. In this sense, the arrow of time becomes strong where structure appears. Because structure creates memory, it leaves records. In a perfectly homogeneous world, there is nothing to talk about. But in a world that builds patterns, there is a past and a future. Not philosophically, physically. Time becomes real where there is difference, organization, irreversibility, and memory. And now connect that back to gravity. If gravity is a response, it does not only ask how much matter is here, it also asks what state is this matter in? How organized is it? How correlated is it? How distinguishable is it? And if we take that seriously, then cosmic evolution reveals an additional connection. From early simplicity, difference emerges. From difference, structure emerges. From structure, the cosmic web emerges, and with the cosmic web, a late epoch appears where the effective gravitational response can become sensitive to that organization. And if gravity is a response, we expect the sharpest questions in the most extreme systems. This brings us to black holes. Black holes are special because they force geometry and information to collide, where space-time becomes extremely compressed, where classical geometry and quantum state descriptions are in their deepest tension. And if gravity is truly connected to the correlation structure of a state, then black holes are not separate stories. They are the extreme case. This does not solve the black hole information paradox, but it can offer a bridge, a language where the link between information and geometry is not forced, but natural. And that takes us to the biggest collision: quantum physics and relativity. The language of quantum physics is state, probability, correlation. The language of relativity is geometry and gravitational response. And if geometry is, in some sense, a response to the state, then these languages may not be enemies. They may describe two levels: quantum physics as the microscopic structure and relativity as the macroscopic response. I'm not claiming we have full unification here, but I am saying this line of thinking points in a plausible direction. The possibility that geometry and information are not independent ideas. And now, the most important sentence of this video. If gravity's late-time response is truly information-sensitive, then cosmology is not only about how much matter the universe contains, it is also about how matter organizes itself. This video does not claim that everything is solved. It claims that there is a minimal idea that could be captured numerically. And if this direction is real, then the next generation of observations will not only refine it, they will decide. Thank you for watching.